you hear the speed of light, the first thing that might come to mind is the movement of light through space. Imagine a world with no speed limit. In this world, everything could connect instantly, without any separation between time and space. However, this leads to a major problem. Space, time, and even matter would cease to exist in the way we know them. The answer to this paradox is the speed of causality, which is the speed of light we are familiar with, 300 barren kilometers in a vacuum. This speed is the ultimate limit of the universe, the maximum pace at which any information or causal relationship can propagate. To understand this, we must go back to the early discoveries of Galileo's principle of relativity, where no velocity is special and all speeds are relative. However, when James Clerk Maxwell developed his equations for electromagnetism in the 19th century, a major issue arose. These equations contradicted the principle of relativity. It wasn't until Lorentz and Einstein introduced a new transformation, the Lorentz transformation, that the deep connection between space and time was revealed, and the ultimate speed limit was established, the speed of light. This is what we now understand as the speed of causality, the speed at which not only light, but all information in the universe must travel. In a world of science, one of the most fundamental and important concepts is Galileo's principle of relativity, a groundbreaking discovery made in the 17th century. This simple yet profound idea states that no velocity is special, and the results of any experiment should be the same, regardless of whether the observer is in motion or at rest. In other words, Galileo pointed out that there is no absolute frame of reference, and all frames of reference are equally valid as long as they are not accelerating. This concept not only changed our understanding of motion, but also laid the foundation for key developments in physics that followed. Galileo's principle formed the groundwork for classical physics, particularly the laws of motion developed by Isaac Newton. Newton's laws of motion were built upon Galileo's principle of relativity, creating a unified system where forces acting on objects and their velocities could be described with simple mathematical equations. In this framework, no position or velocity is special. All objects follow the same laws regardless of the location or speed. However, by the late 19th century, as scientists delved deeper into the study of electromagnetism and the equations of James Clerk Maxwell, new discoveries raised a series of important questions. Maxwell developed his equations to describe how electric and magnetic fields interact. These equations, however, seemed to contradict Galileo's principle of relativity. The core issue was that Maxwell's equation predicted that light had a defined speed, and this speed would not change, no matter how fast the observer was moving. Newton's theories and Galileo's relativity suggested that velocities could simply be added together when observed from different reference frames. But Maxwell's equations revealed that this approach couldn't hold when applied to light. The equations showed that if the observer changed reference frames, the simple addition of velocities would no longer work. This created a significant paradox in science at the time, as Maxwell's equations couldn't consistently apply across different reference frames. This paradox was resolved with the arrival of Albert Einstein and his special theory of relativity in the early 20th century. Einstein realized that, in order for Maxwell's equations to be valid across all reference frames, a new transformation was needed, which he called the Lorentz transformation. This discovery showed that space and time were not separate entities, but deeply interconnected and could change depending on the observer's speed. The Lorentz transformation not only resolved the contradictions in Maxwell's equations, but also led Einstein to develop his theory of relativity, where time and space were no longer fixed concepts. Thus, Galileo's principle of relativity, while foundational, was expanded and refined to fit the new discoveries in physics, leading to the development of revolutionary theories that changed our understanding of the universe. Einstein's theory of relativity demonstrated that while Galileo correctly stated that no velocity is special, the speed of light is special in an entirely different way. It represents the maximum speed that anything in the universe can reach, setting the stage for a new era of exploring the cosmos in the 19th century. The field of electromagnetism was revolutionized by the work of James Clerk Maxwell, who developed a set of equations that beautifully describe the relationship between electricity and magnetism. These equations, now known as Maxwell's equations, laid the foundation for much of modern physics. They explain how electric and magnetic fields interact and how electromagnetic waves, such as light, propagate through space. However, Maxwell's groundbreaking work also revealed a significant dilemma when it came to the established understanding of motion and relativity. At the time, scientists still rely heavily on the principles of Newtonian mechanics and Galileo's principle of relativity, which stated that all velocities are relative, and that the laws of physics should be the same for all observers in uniform motion. According to this framework, space and time were thought to be independent of one another, and velocities could be simply added together depending on the observer's motion. But Maxwell's equations caused a problem within this classical understanding. They imply that light, as an electromagnetic wave, traveled at a constant speed regardless of the motion of the observer. This was a direct contradiction to the principles of relativity, which suggested that the speed of any moving object should depend on the observer's frame of reference. The dilemma stemmed from the fact that Maxwell's equations suggested an absolute speed for light, a speed that would always remain constant, no matter how fast an observer was moving. This implied an infinite speed of light, which was highly problematic. If light truly traveled at an infinite speed, it would have no delay in reaching its destination, meaning that space and time themselves would break down as meaningful concepts. The concept of cause and effect would lose its structure, and our very understanding of space and time would be upended. To further illustrate this issue, imagine that light were traveling at an infinite speed. This would mean that the time it takes for light to travel between any 2 points would be zero, and as a result, the separation between events in space and time would vanish. In essence, space and time would cease to function as distinct entities. This paradox highlighted a major flaw in classical physics and raised important questions about the nature of the universe. At this point, scientists faced a crucial challenge. How could they reconcile Maxwell's equations with the idea that space and time were relative and not absolute? The answer to this dilemma came with the work of Henrik Lorentz and, later, Albert Einstein. They introduced a new transformation, the Lorentz transformation, which preserved the consistency of Maxwell's equations while also accounting for the principle of relativity. He just outrun hell. This transformation showed that space and time were not independent of each other, but rather were linked in a way that depended on the observer's motion. In doing so, Lorentz and Einstein reshaped our understanding of the universe, revealing that space and time could be altered based on the observer's velocity. This new perspective also led to the discovery of the speed of light as a fundamental constant in nature, representing the maximum speed at which information and causality can propagate. The resolution of Maxwell's dilemma ultimately contributed to the development of Einstein's theory of special relativity, which fundamentally altered our understanding of space, time, and motion. Thus, while Maxwell's equations were groundbreaking in their own right, they exposed deep inconsistencies in the classical understanding of physics. The resolution of these issues by Lorentz and Einstein helped to reconcile electromagnetism with relativity, leading to the modern conception of space and time as a unified entity, and establishing the speed of light as the ultimate cosmic speed limit. To resolve the inconsistency between Maxwell's equations and the principle of relativity, scientists needed a new transformation, one that would replace the Galilean transformation that had been in use for centuries. The solution came with the Lorentz transformation, developed by Hendrik Lorentz and later applied by Albert Einstein. This transformation not only preserved the consistency of physical laws, but also fundamentally altered our understanding of space and time, laying the foundation for the theory of relativity. Especially in explaining the speed of light, the Lorentz transformation demonstrated that space and time are not separate entities, as previously thought. Instead, they are deeply interconnected, contrary to Newton and Galileo's view, where space and time were seen as fixed and unchanging. Lorentz recognized that these quantities could actually change depending on the observer's velocity. This meant that time and space were not absolute, but could shrink or stretch depending on the reference frame speed. One of the key revelations of the Lorentz transformation was the concept that the speed of light is constant, no matter how fast the observer is moving. This discovery solved the problem of the inconsistency between Maxwell's equations and the principle of relativity. It also introduced a new way of understanding how objects and events in the universe interact with each other. By applying the Lorentz transformation, the equations of physics could consistently apply across all reference frames, providing a clearer picture of how space, time, and velocity interact. The Lorentz transformation was a critical turning point in understanding relativity, particularly in explaining that the speed of light is not the speed of any physical object, but the maximum speed at which information and causality can propagate to the universe. Thanks to Lorentz and Einstein, not only were the contradictions in electromagnetism resolved, but a new theoretical framework was established where space and time are intricately linked, expanding our comprehension of the universe. The Lorentz transformation, developed to address the inconsistencies in Maxwell's equations, not only helped reconcile electromagnetism with relativity, but also provided a deeper insight into the fundamental structure of the universe. One of its most profound implications is the prediction of a universal speed limit, denoted as c, which is the speed of light. This speed limit is not just the maximum speed at which light travels, but also the fundamental limit for how quickly any two parts of the universe can communicate with each other. The Lorentz transformation showed that space and time are not interdependent, but rather are interconnected. This means that the speed at which information or causality can travel is constrained by a universal maximum, the speed of light. No object, signal, or interaction can exceed this limit. This principle ties into the concept of causality, which is the relationship between cause and effect. For any two events to be causally connected, the effect cannot occur before the cause. The speed of light sets the boundary for this causal connection, dictating the maximum rate at which cause and effect can propagate across space and time. By predicting this speed limit, the Lorentz transformation also clarified the nature of massless particles, such as photons, gravitational waves, and gluons, which travel at the speed of light. These particles, having no mass, are not hindered by any resistance to motion and can move at the maximum possible speed. This is a direct consequence of the laws of causality, as any faster speed would violate the fundamental principle that the cause must precede the effect. Ultimately, the Lorentz transformation plays a crucial role in our understanding of both electromagnetism and relativity. It defines the maximum speed at which any information or causal relationship can propagate, establishing the speed of light as the ultimate cosmic speed limit. This concept of causality is not only a cornerstone of modern physics, but also shapes how we understand the very fabric of reality, where space, time, and the flow of information are intrinsically linked. The speed of light is not just a number representing how fast light travels through space. It is the maximum speed at which massless particles, such as photons, gravitational waves, and gluons, can move. This stems from an important principle in physics. Mass impedes motion. Particles without mass, free from the resistance that mass causes, can reach the maximum speed allowed by the universe. The speed of light, mass, is a crucial factor in determining how an object moves. The larger the mass, the more difficult it is for the object to accelerate, because the force required to move the object increases as its mass increases. For massive objects, this means that achieving high speeds becomes progressively harder, as it requires an immense amount of energy to overcome the resistance created by the object's mass. As a result, objects with mass cannot achieve the speed of light because it would require infinite energy. In contrast, massless particles, such as photons, light particles, gravitational waves, and gluons, are not bound by mass, allowing them to reach the maximum speed possible in the universe. The speed of light, this ability to travel at light speed, allows them to move without any hindrances from the effects that mass causes on motion. These particles are the only entities in the universe that can travel at this speed without encountering any obstacles related to mass. The ability of massless particles to move at the speed of light is key to understanding the workings of the universe. For example, photons, which are the carriers of light, travel through space to convey information, playing a fundamental role in connecting the elements of the universe. Similarly, particles like gluons and gravitational waves are essential for transmitting forces between particles and enabling interactions within the universe. Therefore, the speed of light is not just a physical number, but also a core concept in understanding the universe and causality. It is the maximum speed at which massless particles can move, enabling a range of discoveries in how space, time, and forces in the universe are interconnected. Understanding the speed of light and why massless particles can move at this speed is an integral part of constructing theories like relativity and particle physics. If the speed of light were infinite, e.c. infinity, it would lead to paradoxical and inconsistent outcomes in our universe. One of the most significant consequences would be the collapse of the concepts of time and space. With no limit on the speed of light, information and causal relationships would be transmitted instantaneously, leaving no delay between cause and effect. This would completely disrupt the structure of time and space, rendering them meaningless. Furthermore, cause and effect relationships would become undefined because all events would occur simultaneously, making it impossible to distinguish between what happened first and what happens later. For instance, in a world where the speed of light is infinite, you could witness two events happening at different points in the universe almost simultaneously, with no time difference between them. However, this contradicts the principle of causality, where the cause must precede the effect. If light could travel infinitely fast, everything in the universe would meet instantly, and we could no longer determine the cause of an effect, undermining one of the fundamental principles of physics, the existence of a finite speed limit. The speed of light is crucial for the universe to function as it does. This limit ensures that causal relationships are preserved and that time and space can still be distinctly measured. When the speed of light is finite, information and events can only occur within a specific time frame, allowing for a separation between events and creating order within the universe. The speed of light is, therefore, a vital factor in maintaining consistency and order in the universe. Without this limit, time and space would blur together, and it would be impossible to determine the sequence of events. In fact, the existence of this maximum speed is not just a physical concept, but a necessary condition for the universe to exist as we understand it, since everything in the universe follows the principle of causality. The speed of light provides a crucial boundary to maintain the stability and structure of the cosmos. The Lorentz transformation led to Einstein's famous results in special relativity, including time dilation, Liv contraction, and the equivalence of mass and energy in mixture. These groundbreaking results not only revolutionized theoretical physics, but also completely altered our understanding of space, time, and matter. One of the key outcomes of special relativity is the phenomenon of time dilation. According to Einstein, time is not an absolute and fixed quantity. Instead, it can slow down for an object moving at speeds close to the speed of light. This means that for someone traveling at high speeds, their clock will tick slower compared to someone at rest. This effect has been verified through experiments with atomic clocks and has become a cornerstone in modern physics. In addition to time dilation, special relativity also explains the concept of length contraction. When an object moves at speeds close to the speed of light, its length shortens along the direction of motion. This can be imagined as a long object being compressed as it travels at high speeds. This effect only becomes noticeable when the object moves at speeds close to the speed of light. Another significant discovery is the equivalence of mass and energy, expressed by the famous equation m². This equation shows that mass and energy are two forms of the same entity. Energy can be converted into mass, and vice versa. This principle explains why nuclear reactions, such as those occurring in stars or atomic bombs, can release vast amounts of energy from a small amount of matter. These results of special relativity transformed how we perceive the universe. They demonstrate that space and time are not independent, but are interconnected and depend on the observer's velocity. Einstein's theory of special relativity has not only reshaped physics, but has also had profound impacts on various other fields, from technology such as GPS systems to how we understand the movement and existence of the universe itself. If there were no speed limit, the universe would become a paradox with no real structure. Without any boundaries on speed, mass would require infinite energy to exist, which is impossible. Everything in the universe would fail to move or even exist without a speed limit, and as a result, there would be no distinctions between different points in space and time. Everything would become simultaneous with no cause and effect, no past, present, or future. The universe would lose its order and connections, and nothing would distinguish one event from another. From these physical concepts, we can derive a profound life lesson. Limits and boundaries, although sometimes they feel frustrating or restrictive, are actually the elements that provide structure and stability in our lives. Just like the speed of light in the universe, the limits we encounter in life help us find direction and keep things from falling apart. When we learn to accept and understand our own limitations, we find true freedom in growth and overcoming challenges. What do you think about this idea? Share your thoughts in the comments below. And don't forget to subscribe to the channel so you never miss out on more fascinating videos. Together, we will continue to explore the amazing world of science and life